Can you see? I'm projecting. Can you see, all of you?
Yes, sir.
Yes, sir.
Yeah. So in the last class, I had this is your average occupation number, isn't it? N average is given by this expression. So if you plot it for some finite temperature, it will look something like this, isn't it? And if I plot it for, say, higher temperature, what will happen? It will look something like this, isn't it?
Yes, sir.
And if I plot these two together, so can you tell me which one is higher temperature, which one is lower temperature? The Fermi function or the average occupation number. The blue one is higher or the red one is higher? Temperature.
Red one.
Yeah, red one is higher, isn't it? So I can think that this is like your conduction valence band. This is your conduction band. But as the temperature increases, your Fermi function leaks into the conduction band. Okay, this is very qualitative, of course. So actually, you can create an animation like this shown here, and I just change temperature. Beta is 1 over temperature, isn't it? So beta small means high temperature, and beta large means low temperature. Okay. So let me play this. This is at some high temperature. Now I'm lowering the temperature, increasing the beta. Beta is 1 over kVt. And this is what do you expect, isn't it? This is what you expect. When you lower the temperature, what do you expect? You expect this. This is fine?
Yes, sir.
I can do the other thing. Here, I'm increasing the temperature. You see? Can you see? Again, I'm increasing the temperature. Again, I go back to very low temperature and increase the temperature. Or other way I can play, of course. I can decrease the temperature. So as you decrease the temperature, it becomes more like a step function, isn't it? At t equals to 0, it is exactly a step function. So I can also calculate this at different temperature. Now, can you tell me which one is at which temperature? The obvious that the blue one is at some temperature which is high, isn't it?
Yes, sir.
This dark yellow one is slightly smaller temperature. This green one is even smaller. The red one is even smaller, like this. So you understand, no, what will happen to this function as you change the temperature. Now this
Yes.
function is n average essentially. So actually what I did not do, today I did not do in the course, I did not calculate the partition function for the Fermi gas or for the Bose gas. So I hope that you guys can go and try to compute the canonical partition function for the Fermi gas. What should be the canonical partition function for the Fermi gas? Tell me. Any idea? How do you proceed? Because I'll just take few more minutes and then we'll go to assignments. Tell me, how do you calculate the partition function, the canonical partition function for Fermi gas? What you should do? Can anyone tell me? See,
Can
you
it
have
go
yeah.
something like sum over I 1 plus a plus e power minus beta epsilon I into z inverse.
So basically, what you see, no, that is not z inverse. So your z itself actually, or the q, whatever the notation you use, the partition function, it is sum over. What is the formula? Sum over exponential of minus beta ei, isn't it? Sum over I, or sum over
Canonical.
n, sum over n. Yes.
Yes.
What are the values of n? What are the values of n? Tell me, for fermions. What are the values of n?
0 or 1.
0 and 1, two possible values of n, isn't it? So actually sum will have two terms, isn't it? One is for n equal to 0, one is for 1 equal to 1. Is it clear?
Yes.
So n equal to 0 means exponential of 0, which is 1. So if I carry out the sum, it will be 1 plus another exponential function, no? But what is the Hamiltonian? That is the question, $1,000,000 question. What is the Hamiltonian for this Fermi system?
Square over 2m if you assume particle in a box.
Yeah, p square over 2m if you assume putting in a box, but I am not using this kind of formalism. Actually, if you think carefully, very carefully, actually you will see that your Hamiltonian is nothing but your epsilon minus mu in the bracket times n. N is the occupation number. So that is your Hamiltonian. So your exponential is minus beta times epsilon minus mu, which is in bracket, times small n. Is this clear? So epsilon minus mu is something like energy per particle kind of thing. Okay, epsilon minus mu. And you have n is the occupation number. So epsilon minus mu, if I multiplied with the occupation number, that will give me the effective Hamiltonian for the system. Okay, I'm not going to do it. I'm just giving you hint. So now you can calculate the partition function, isn't it? You can write down what I'm saying. What I'm saying that your partition function will be something like your Hamiltonian is, this is your Hamiltonian, say, is your something like epsilon minus mu times n. This is a Hamiltonian. Okay. What is the partition function? The partition function is going to be exponential of minus n epsilon minus mu, of course, and then you have to multiply this with beta. Okay. But this is not the same. You have to sum it over. Sum it over possible values of n, and n is, this is how it is. Okay. So this is the answer. Is this clear that this is the answer? This is 1 plus exponential of beta times mu minus e. Okay. So this is your partition function. Okay.
So this is one
clear?
particle partition function?
It is, you can think it is a one particle partition function, but actually you have n number of particles. It's not a one particle partition function, I would say. Because it is, yes, one particle, because epsilon is per particle. But it is actually, when you talk in terms of, it's a continuous variable n, no? It varies from 0 to 1. It is actually, everything is in the language of occupation number. So actually you have n number of particles, of course, you have n number of particles. Okay. And from here you can calculate the n average. How do you calculate the n average? It's not very difficult, no? You have to calculate the distribution, the probability distribution for this fermionic system and multiplied with n integration sum over 0 and 1. That will give you n average, isn't it? You can go and check. Your n average is 1 divided by 1 plus exponential of plus beta into epsilon minus mu. If you go and check, isn't it? Go and check. That is your n average.
Yes.
And this n average you can also calculate starting from this fermionic partition function. So I am not doing it, but just you can go and have a look how it is done. Okay, I'll not do it today now, but next thing, we can discuss some of the problems in the assignment, and I think what I'm going to do, you guys can ask me which one you want to discuss. Maybe we'll discuss that, but I'm not going to discuss that. It is going to be discussed by Kaushik. He is going to present. He is going to present, and so he can do that. So Kaushik is there. Kaushik, you are there, no?
Yes, sir.
Yeah. So now, before you present, let me ask. So which one? So we have many assignments. Which one should we look at?
8, 9, sir. I have written in the message.
chat box.
Okay. So assignment number 8 and 9. Okay. What else? So let me check. Did you get my email today? Morning email. How the exam is going to be?
Yes, sir.
Yes,
We
sir.
have.
You understand, na? People who have taken my earlier course, they would know. So this is your assignment 1, no? So let us see. Okay. Which one? You want to see only 8, 9?
Question number 11.
Sir, and 13 and 15 also.
11, 13 and 15. 15. Okay. So maybe now this guy can discuss. Someone is saying 8, 9. So let us 8, 9, 11, 13, 15. So these 5. So hopefully we'll have time to discuss these 5. So let us start from, okay, 8. Start with 8. So can you do that, Kaushik?
Yes, so I'll
So you can present. Can you present?
int f, yeah.
I hope I don't need to give you any permission. You can present, I think. Try.
Yeah.
Just see that.
There is some. Yeah, it is. I cannot share your screen. So,
Why? It is not. I'm not allowed. What?
Firefox might not have screen recording permission on your computer.
What?
So there is a, okay. So it is showing, the message is showing Firefox might not have screen recording permission on your computer. Okay.
It should be possible. Otherwise, I have to share.
Okay. Can you please share?
But I am not going to teach.
Yeah,
Okay.
I'll so,
Yes. You do it.
yeah, yeah.
You can share if you give him the permission. There is a thing that the host has to give him permission to share the screen. If
But
you
I
give
don't
him
think it is
the
because of that. It is because of some other thing.
no, that is an issue because I have had this before. Once I was presenting elsewhere, that the host has to give him a permission. There's a settings option.
Okay.
Yeah.
Try. I don't know.
Yeah, it is still,
Can
I'm
you?
not able to do that.
It is your Firefox problem. I know. So what I'm going to do, I'm going to present this here. What is 8? Number 8. Number 8 is this.
Yes, yeah.
Can can you email me?
Okay.
Let me. Okay, I'll do it. You already emailed me, no?
Yeah, I already had.
Okay. So you have already emailed me.
So it is written assignment 1.
Ah. Okay. Yes, I have got it. Yes. 8. Just a minute. Yeah. Can you see? This is
Yeah.
question number 8. So now,
Yes.
now he is going to explain.
Yes. So,
Okay. So I will not talk.
okay. So,
He is going to talk now.
so this question number 8, it is, yeah, it is about that in the n number of non-interacting harmonic oscillator, and we have to calculate the microcanonical partition function. So can you hear me?
Yes, we can hear you.
Okay, okay, okay. So that means what we need to do is first we need to know what is the Hamiltonian. So for ith particle, you can see in the equation 15. Second term is the potential energy for the ith particle. So there is n non-interacting particles. So we have to sum over all the particles. Okay. So this is the Hamiltonian. Now it is a microcanonical ensemble. That means the Hamiltonian has to be of energy E. Okay. So in 16, equation 16, you can see this partition function is given by this delta function. That means only the total energy E is accessible. Okay, and then we have to integrate over all the, that means whole phase space. So all over Q and P, and there is this volume, that means E0 by epsilon. This is just a normalization constant. And so what we can do, we can rescale this term, then P square by twice m, and this kinetic energy and the potential energy, so that you can see this Hamiltonian will be non-dimensional. That means it can be, we take pi by root over of twice mi, some that means variable gi, and then wi some square root of ki by 2 ri. Then it will be just then you can see in equation 17, it will be j square by w square. So this is the rescaling. Okay. So if you do this rescaling, that means this integration over the integration in 16, then this this dp and dq, that also be rescaled, right? And then this term actually, this omega I term and this yes, this omega I term will be appear actually in this integration as a sum. Is it okay? This is the omega is actually this.
So any question? So how many of you understood? This is Hamiltonian. Everybody understands, na?
Yes, sir.
Yeah, kinetic energy plus potential energy. You sum over all particles, n number of particles. The constant is this. Hamiltonian has to be equal to total energy E. So you put a delta function. You know, this is the partition function in microcanonical ensemble. You know this, no? This is taught in the class. You divide by
Yes, sir.
1 by 2 or 3 and also multiply with E naught to just take care of the dimension. And now you convert this into new variable, nothing else. Don't write p square by twice m. You just write it j square. Don't write kr square by 2. Write it w square, isn't it? You just convert. So accordingly, p and q will be converted into j and w. Any notation you can use. Okay, you can use a p tilde, j tilde, q tilde. That is also fine. Okay. So essentially, same integral is written like this. Okay. When you write down this, you also you see that because you have this omega I should come here. This omega I sum over omega I, because
This is root over ki by mi.
yeah, because this one is omega I actually according to him. So
Actually, the above 16, this omega equals to root over ki.
this one, no? This is half omega square actually.
Yeah,
So
yeah.
omega is root over ki. So you put that. So essentially, this integral look like this. The structure is as follows: delta function of r square something square minus some constant, isn't it? And then you have this, and then you can use the formula. And there's a formula of delta function. If you have delta function of something square minus something, it is given by this: delta function of that quantity minus square root of this e plus delta function of the same quantity plus square root of e, and then you have to divide it by 1 by twice root over e. Okay, this is a formula for delta function. So you have a delta function of x square minus constant. So it is actually delta x minus root over that constant plus delta x plus root over that constant divided by 1 over 2 times root over that constant. This is just a mathematical identity for delta function. Okay, is this clear? And then so basically this integral will be divided into sum of two integrals. One is this delta function, another one is this delta function. Of course, this multiplied with some constant. And then you can integrate it, isn't it? Because integration of delta function is not difficult. Now he'll tell you how it is done.
Yeah, so actually there is a question number 10. So question number 10, I actually write it explicitly. That means why should we avoid one, neglect one delta function? So
Okay.
can you show this?
Question number 10.
Yeah, that means just below. Yeah, this. No, yeah, question number 9.
9.
Yeah.
Yes. Okay.
Yeah, so
Yes.
can you go down a little bit?
Yes.
Yeah, so it is a similar form. Now that means this 26, that means here it is p square by twice m, and there is a, that means another term. But we consider this summation over pi square plus this potential energy as a phi I or ri in it, and the r square. Here we have considered r square.
So his point is it has same structure.
Yeah.
Anish and Kailash and others, you can see same structure. Only you have this only p square by twice m converted into some function the phi I square. Okay, some square minus this. But here you have a sum over I. You understand what I'm saying?
Yeah. So this phi square now we can take it as r square.
Some constant square,
some-
yeah, something square, yeah.
Some constant. Okay, and then so it is actually you can see a 3n dimensional spherical coordinate. So there will be 3n minus one number of angular coordinate and one polar coordinate. And in this case, that means in this free particle case, there is this there is no dependence on. Okay, I already said. So this is angular part, and this is the spherical. That means in 26, there is a polar coordinate and there is a angular coordinate.
See, what he is saying that when you integrate for free particle over the momentum, okay, this is a momentum, this is p is converted into y, but before that, you have this equation number 23. You have momentum as well as position.
Yeah, that is
Position. If you for each position you have a small v, so there are n such thing, no, a capital V. Okay, this notation. So then v to the power of n. You understand this, no? Each one is v. This integral. How many integrals are there? N number of integrals, capital N number. So v to the power of n is this integral. All the position coordinates integrated over. Okay, the free particle, there is no position coordinate in your Hamiltonian. So this integration can be carried out independently. Is it clear, Anish and Kailash? It's not a very difficult thing because each integral will give you v, and there are n number of such integrals, so it will give you v to the power of n. So you had this E0, it has picked v to the power of n divided by n factorial h to the power of 3n. This is fine. Now left with this integration over momenta coordinates, and then this, and then you make use of the trick of whatever the delta function, and you come to question number 26. It's not very difficult.
Yeah,
but
so
you should understand that how you from phi 1, phi 2, phi 3, phi n you get this. Can you tell me? Can you tell us why? Why this volume?
So we are going from this Cartesian to polar coordinate. So if you do that, that means in the polar coordinate there will be one radial coordinates and 3n minus one number of angular coordinates, and so and the volume element should be this kind of thing. That means this is the structure actually. R to the power 3n, like in 3 dimension it is r square, then 3 minus 1, and there is two angular coordinates, theta and phi. So it is the generalization of this 3-dimensional coordinate. So it is 3n dimensional coordinate. So it is actually, the volume element will be r to the power 3n minus 1. This is the polar part into dr, and then there will be the integration over all the angular coordinates.
So actually, let me tell you. So do you remember this? In hydrogen atom problem, you have sine theta, cos theta, sine theta, d theta, d phi, r square sine theta, d theta, d phi. Remember this? I think
Yes,
everybody
sir.
remembers.
Yes, sir.
You go from
Yes.
x, y, z, you get this. Essentially, it is so. Essentially, you have a r dependent part and a theta phi. So theta phi is here, embedded here in omega. Okay, generalized. And r is this. Just put n is number of particles. You have one particle. Then what is the value of n? N is 1. It will be r to the power of 3 minus 1, r square. You remember, you get r square, isn't it? R square sine theta, d theta, d phi. So this part is again becomes d to the power of like 3 into 1 minus 1. So d second d square omega. Now d square omega is actually this is nothing but your sine theta, d theta, d phi, because you have two, d theta and d phi. You understand? This is more generic way of saying writing. More generic way of writing. General, if you go from x, y, z of n particle system to r and omega n particle system. This is the conversion. Okay, Anish, Kailash, Pooja, everyone. And
Yes,
that
sir.
will
Yes,
become
sir.
like this. I understand that you don't understand it fully, but since you are coming from chemistry, you don't have that background in mathematics. You may have problem, but you can go back and check. But this is how it is. But I can put an analogy between this and the one you have learned in hydrogen atom problem. Okay, so now you can proceed, Kaushik.
Yeah. So now the next page,
Hmm.
page number 8. So there is a formula for this integration of our angular coordinates. So you just check it. This if n is 2, then you will get these 4 pi things. Like
This is a gamma function. This is the definition of gamma function. Okay.
yeah. And
I
then
used to,
this gamma is actually this is gamma
yeah.
function is given by this.
You
So
remember that in my Fermi, this Bose-Einstein function, we put this gamma function. I did not explain, but this is how it is, gamma function. Definition of gamma function. You must have learned during your, if you had math in BSc, you must have learned this, I'm sure. Anyway, not everybody. Anyway, yeah, please proceed.
yeah. So this integration then in the 26, that means integration of our angular coordinates in 26, you can do it easily. That means this using this formula actually, d omega formula, integration of d omega. And if you do that, then you will get some this 2 pi n by 2 and this gamma function. Then the prefactor as a prefactor in the equation 27 in the first line. Okay, and you have to do this integration over dr r. Okay, and so now this delta function can be written as I said, that means as a summation of this. That means there is a 2 peak at minus delta e and then sorry minus root square e and plus in root square root e. And you can see r is varying from 0 to infinity. That means r cannot be minus root e, right? So this in the second term, delta r plus square root e, that term it will not contribute to the integration. Okay, only r equals to root e that will contribute.
Yes.
Okay, so you put this. Then delta function means in a function integration of our in function with delta function means this function just take this value. That means at this point. That means
Yeah,
r
what you need to do, you need to replace your r with root over e. So it will be
over.
r to the power of 3n minus 1 divided by 2. Okay. Sorry, e to the power of 3n minus 1 divided by 2. But e to the power of 3n minus 1 divided by 2, I think n is very large. So it is very close, very close to 3n minus 2 itself, isn't it? This approximation, you look at it. And you put it here. Okay.
Yeah, so now this gamma function can be approximated by this as this Stirling approximation.
Yes.
And you can neglect this plus 1 because n is very large. And if you do that and then put this all this stuff, then we will get the 20. I think they will be straightforward.
Okay, it is not a very difficult, but these two things are very related. Can you see that? So why I put this assignment? Can anyone tell me why I put this assignment? I want you to learn something from this assignment. What is that? Not the math, but something about physics. something on the physics. Can anyone tell me?
We can use any of the part means any of the ensemble
Yeah, very
micro
good. Very good.
chemical any of
Who is this? This is
Nashit.
yeah. So actually, indirectly, I'm telling there's something called equivalence of ensemble. We did in the class, no? For I think we did it for NVT, canonical ensemble, no? P is equal to RT. We did, no? P is equal to NKVT. We did that. Ideal gas. Did we do that
Yes.
or yeah?
Yes, sir. Yes,
But
sir.
here we are doing the same thing, but working in microcanonical ensemble. It is more involved, no? The integrations involve delta function and other things. Conceptually, it is, and also microcanonical ensemble is not easy to achieve experimentally. But what it shows that it is equivalent. Actually, if you can do the math, then you can also get the same result in microcanonical what you get in canonical. But in all the chemistry courses, it is usually you're taught canonical ensemble and then don't even mention properly there. But then you calculate quantities in that ensemble. So what I am calculating this in microcanonical. So these 2 or 3 problems I deliberately put from microcanonical ensemble to show that you can get the same result what you get from canonical ensemble. Is this clear? This is very nice and you should appreciate. Don't think about the
Yes,
exam
sir.
all the time. Also think about what you learned. So now you go back to the previous question. Maybe this question could have been put after this, but it is very similar. Only you have another term here, no? This is harmonic oscillator essentially. It is harmonic oscillator, isn't it, Kaushik?
Yes, it is harmonic oscillator.
The first one is the next one is free particle. This one
Yeah.
is harmonic
Harmonic.
oscillator.
Yes.
So I don't think he should go through in detail. What I'm going to do, we can email this after the class. Okay, I'll email this. Not email, I'll put it in the folder. Okay, you can have a look. Is this clear?
Yes, sir. Next
Yes, sir.
11 and 20.
Just try tonight. Do yourself. Okay, you'll find out. It's not very difficult. It is difficult for the first time, and then it's not difficult. Now, question number 10. Okay.
Yeah.
So this is a question number 10.
Yeah. So this is actually it is the canonical partition function for
This is again canonical rotation function. Yes, yes.
for the monoatomic ideal gas is given here. So
In one of the question, there was a typo, no?
yeah,
Kaushik?
this is in crystal. Then the question regarding crystal.
What are the typo? Some two
So,
factors.
yeah. 2 factor is the extra 2 factor is there.
There. Okay. Yeah. Okay. So you have corrected that, no?
Yeah.
Huh?
Yeah.
So yeah. Anyway. Yeah, you can explain this problem to them.
Yeah, so the pressure is actually you can easily calculate from this if you know the partition function using this formula, then KBT after the 29th. And then
See, you have to see the structure. Just see, all of you see. V to the power n, what does it tell you? Anywhere it basically means there is no interaction. No, because this is coming from n number of integrals over coordinate for each particle, n particles. So these particles, they don't interact. They are not interacting. Ideal gas kind of thing. That's why it is over n, isn't it? Is this clear?
Yes,
Is this
sir.
clear? And 1 by n factorial means I'm taking care of this indistinguishability. And this one, this is a translational partition function. So essentially, it's a quantum gas, but not a fermion, not a boson, but it's a semi-classical kind of thing. I'm taking care of indistinguishability, but I'm like they are not explicitly treated as boson or fermion. Is this clear?
Yes, sir.
Yes. So now you know the partition function, and pressure is given by this, and this is simple algebra or whatever calculus.
Yeah.
So see, this is the physics. This average energy is 3/2 n kVt. Your equipartition, you that end of the day you get that, isn't it? End of the day, get that. So and the structure is like this: function of temperature times v to the power of n. Function of temperature times. See, temperature is always coming from the momentum part. You see, check. Someone is trying to. No, I cannot. Okay. So temperature is okay. Coming from the momentum part, and the v to the power n coming from the coordinates, the other part. Okay, the configuration part. Is this clear? This is not a very difficult question. This question number 10. I think people did not ask question number 10. They asked,
Yes, sir. We already solved that question.
they asked question number 11. Some of you.
11 and 13 and 15.
Okay. Where is the typo?
Yeah, so this there been e to the power minus h by 2 kbt. This denominator has a typo. That means it will should not be 2 there.
Which one? This one?
Yeah.
Oh, then you change it actually.
Yeah, actually in the solution I have actually changed this partition function, deleting it and
Okay.
okay.
Okay. Now you proceed.
Okay.
Okay. See, before you proceed, you just look at it. You can clearly see this is partition function for this part is translation, this is rotation, this is vibration, isn't it? You can see that, isn't it? You can see that. But
Yes, sir.
Yes. But this part is electric field, because if I this part has to be coming from the electric field. Okay. So we'll see what is that. So because you have a magnetic moment, this is a magnetic system, so you have a not a magnetic system, it's a Dirac molecule, so it will align with the electric field. So this is a partition function in the presence of electric field for this diatomic system. Okay. Now this now Kaushik can explain. Yeah, Kaushik, please explain.
Yeah, so this the free energy. So we need to calculate the magnetization, and magnetize the conjugate is actually this electric field. Okay, so we can get this magnetization if we I mean
You
know
understand
the
this conjugate thing, na? For example, what is the conjugate of temperature?
Entropy, yes.
Has to be. You see, always you signed SDT TDS, isn't it? What is the conjugate of pressure?
Volume.
Volume. PV, PdV or VdP. You get always, isn't it? So like that. So conjugate of magnetization is your electric field. What are you saying? That's I. Yeah. Please proceed.
yeah. So if we then will keep all these other variable constant, and if we do the derivative, then we will get this magnetization. So in this equation, that means
It is not an electric field, it is a magnetic field. No? Why would I call electric field? It's a magnetic system, no? It says electric field.
yeah, it is actually electric field.
I think it is better to say external field, no?
Okay, maybe
Anyway.
dipole things. That means,
Because I understand, because it is like a dipole.
Yeah.
They're calling it. Anyway, please proceed.
Yeah.
Yeah.
So now free energy can be calculated from this the partition function using this minus kBT lnq. That's the standard formula. And you have the Q is given there, and only this xi dependent is the sine hyperbolic part, and this kBT by eta xi, and other stuff is the Vt and dependent part. So we can deal with this only this the xi part, and if we do the derivative, then it is just the mathematics. You can do that. And,
Yeah, it is. See, let me tell you, this is your partition function, no? And then you can do this math. It is not a difficult thing to do. Okay, you should be able to do. What was your problem? This is the problem I think you had, no?
Yes, sir. Exactly.
I understand, because the problem is with the physics. So now once you have it, then you know, because A is minus kVt lnq. So always lnq is minus kVt, A by minus kVt, minus beta kVt. This is how actually. So actually what I'm going to send this. I'm going to put this in the immediately after this class. This will be quite useful, because Kaushik has solved all the problems. Okay. And this is the kind of problem you should be doing. You should not be doing, I don't know, simple problem. Then you don't learn the subject. Okay. Don't worry about the exam day after tomorrow. You can use calculator if you want. One thing I have forgotten, in the exam, please, before the exam start, you show your I card. Roll number. Just hold it.
Sir, actually, I don't have an iCard. I'm a new entrance.
Yeah. So okay. So basically, people who have it, they can show it. Okay. Anyways, so this is how it is. Is it clear?
Yes, sir. Absolutely.
Yeah, because I don't want to spend too much of time here.
Yeah.
Now, this question number 12, what is different from some other question? See, it is this. If I put b equal to 0, a equal to 0, what do you get? Tell me.
Ideal gas equation.
Ideal
Ideal
gas.
gas
So
equation.
this is essentially for a van der Waals. If it is not van der Waals, something like van der Waals gas, some real gas, isn't it? See, the V minus NB is available because you know this B is the volume of each particle, each atom, isn't it? N times B is the physical volume occupied by each particle. And capital V is the volume available for the whole system. So V minus NB is the free volume and whole to the power of N of that. Okay. And this part is coming because of interaction, isn't it? These particles interact, this alpha N square by V kBT. You remember van der Waals gas? It is,
Yes, sir.
Yes, sir.
you remember, no? It is PV P plus P plus a n square by V plus V minus NB equal to N kBT. Something like that, isn't it? It has to be
Yes,
like
sir.
that.
Yes, sir.
You can see these things are appearing here. So basically, if you work properly from here, you can calculate the equation of state for the gas. Okay, then approximate partition function. Yes.
Yes. So here also we have to calculate this phasor. That means the equation of state, then we need to calculate the phasor.
Exactly, this is what you get, no? You can do it. So that just by looking at the mathematical structure, you should be able to see what is this. You get, okay, please get used to. This is very important, huh? You understand my point, no? What I'm saying?
Yes, sir.
Yes. So it is very important that you get used to. So then you do the math, you know, all these things you can calculate. You see, average energy has to be 3/2 kVT minus something, no? Because of the interaction. This A n square by V. Depending on the sign of A, it will be more or less. But heat capacity, see that it has, this part has no temporal dependence. Heat capacity does not change in this case. In this case, okay. Now you want to discuss question number 13 also.
13 and 15, sir.
13 and 15. So
Okay,
yeah,
so,
yeah. Please please explain, Kaushik.
So there is n independent particle and they are in a weak external field H. So first let me take one independent particle. So for one independent particle there is the moment are from minus j to plus j, okay? And so what you can do, so the interaction energy will be at j moment will be minus j mu h, okay? This is the interaction energy. Okay, and then we can calculate the partition function using this e to the power minus h, beta h. Okay, that we have done in the first line of the 36. And then there is some mathematics symbol. That means this is the geometric series, and you can use the formula for sum of for this geometric series. You can get this actually sin hyperbolic function. That means is the mathematic or anything?
No, this is very easy. You know that what is sine hyperbolic function. How many of you know? Sin x, you know?
Yes,
Yeah.
sir.
Yes.
Sin x is exponential of ix minus exponential of minus ix divided by twice I think. And what is the relation between sine hyperbolic x and sine x? Tell me. Sine hyperbolic x. You know that sine of imaginary x is what?
Instead of
Equal to? If I replace x with ix, what will happen? I times
you
x.
get I square
Imaginary
x
I.
and I minus S square.
No.
I
I
see.
am saying that, Kaushik,
Yes.
if
Yes.
I replace the argument that x with
Yes.
I times x,
Yes.
it will be sine of ix. Sine of ix is what?
Yes. Then it will be sine function actually.
This is sine hyperbolic x, isn't it?
Yes.
So basically in the argument exponential ikx, you have to replace that by,
Imaginary.
yeah, I think there's a plus minus thing is there. You can check.
Yeah.
No?
Yeah. There will be minus 1 by twice. Yeah.
Yes.
Right.
So all these things. So essentially, you know, this is exactly what he has done. He has done this, and then
Yeah.
is a
So
partition
for
function.
any binary particle, we have to then take this n times q into q n times, and we will get this that means partition function for n independent particles to the power n. And similarly, then the magnetization is again this conjugate is field. So magnetization can be derived from this free energy. If we then take the derivative with respect to h, and we get the magnetization. Yes, it's magnetization. Okay, so that I've done here. And
Very good,
then,
actually. Yeah, I have not looked at what you have done. Yes. So once you share this document, you should be able to see, all of you. We'll do that. Okay. Now, this 14, I think we need to don't need to discuss. People are saying 15. Can you explain, Kaushik?
15.
Yes.
Okay. So here actually the one-dimensional quantum harmonic oscillator, we have to calculate the average oscillator energy as a function of t. So first thing always to calculate the partition function, and to know get the partition function, we need to get know this energy. So energy is given by this epsilon nu at nth level, given by this. So we can calculate the partition function if we that means the sum over this e to the power minus beta h term over nu is varying from 0 to infinity, and you can get this actually sine hyperbolic term, 1 by sine hyperbolic term. So you know the qt, and then from this qt you can calculate the average. I mean, this is the formula.
Even you can take this, na. Don't go to hyperbolic. Everything you do, end up that you do convert. All this trigonometric actually identity we are using. And delta E is this.
Yeah, and delta is given by this. That means you can.
Yeah. And then you take when kbt is less than h cross omega, cot hyperbolic function is this, it will be 1. Okay, sine value will be this. You can put all these things. See that nice, very nicely done, and you can see that you get average energy equal to kbt and delta E is equal to kbt. Okay. I hope everything is fine, because Kaushik, I have not checked some of the problems because I did not get time. Any other question? How many are there? 18 people are there.
We go to question number 2.
Question number 2.
I think it was 2, if I'm not wrong.
This one.
Yes.
Yeah. So yeah, this is the time derivative for angular momentum, and it is given that Hamiltonian and angular momentum are conserved. That means you can say the Poisson bracket of H and Ln is 0,
Yes.
right? And that
You
means
understand na, that it is a constant of motion, then its Poisson bracket with the Hamiltonian has to be 0.
Yes.
yeah.
Yes.
And if you do
And
that,
derivative 0. Okay.
okay, and there should not be this partial. That means in the equation for it should be total derivative actually, dln by dt. That means in the first part it is written dln by dt, but somehow
This one.
yeah.
So can you check this? Can you change it?
Yeah, I'll change it.
Change it and then email me. I'll upload.
Yeah.
You do it now, huh?
Yeah.
Okay. So any other question? Because I
Sir, what
don't.
hyperbolic,
What hyperbolic?
sine hyperbolic or cos hyperbolic?
Yeah.
What?
Yeah, this is very simple, na? Sine hyperbolic. Sine x you know, na?
Yes, sir, that we know.
Yes. So hyperbolic is if you change the argument to imaginary argument, that becomes hyperbolic. The relation. You understand what I'm saying? That if
No,
you
sir.
very simple. Go to Wikipedia. Don't look at this. Should be there. This is your expression for sine hyperbolic x. exponential of x minus exponential of minus x divided by 2. Okay, if I put x equal to I times x, this will become exponential of ix minus exponential of minus ix. Okay,
Yes, sir.
that is going to be equal to I times sine x, isn't it?
Yes. Minus items.
Yeah, minus I times sine x. Not minus I times. I think I times sine x. Is it minus I times sine x?
Because sin x is actually
I think it's sine x. Sine x is exponential of ix minus exponential of minus ix divided by twice I, isn't it? Check.
yeah.
So there is a relation between, see, okay, maybe it is like that, minus I times sine x, okay. Okay, maybe the other way, yeah. So you can see sine hyperbolic x is minus I times sine of ix. Cos hyperbolic x is cos of ix. So it is coming all from trigonometric identities. Kailash, you understand?
Okay, sir. Yes,
Okay,
sir.
then sine x is exponential of minus ix minus exponential of I plus ix, no? Divided by twice I.
Yes.
Okay. Okay. So likely you can just change it like that. Sine hyperbolic x is equal to sine x. So all this trigonometric identity, nothing else. Is this clear?
Yes, sir.
If I give you this function, this will not look very difficult to you, no? Half
Yes,
time.
sir.
This is actually sine hyperbolic x. I don't know why you don't know. Everybody should know this. This is cos hyperbolic x. Okay, these
Yeah.
are real function in x. Real function in x. Okay, and there is relation between hyperbolic x and sine x like this. Okay, if I take sine of some imaginary x multiplied with minus I get sine hyperbolic x. So basically hyperbolic functions may also be deduced from trigonometric functions with complex arguments. Okay,
Yes, sir.
everybody should know this. Okay, I'll not ask you if you this simple formulae you should remember actually. You should remember. But now Kaushik is going to email me this,
Yes, I'll
this
do.
partial and derivative now. Email me right now,
Yes.
so that in next 15-20 minutes I'll upload this in the folder, and also I'll upload today's video because I'm also recording. Okay, I think I will not continue further today.
So I have one request.
Yeah.
Is
Tell
it
me.
possible to extend the submission time till 8:10 so we get 2 hours full of writing time? I mean, matter of 10 minutes, but if that is okay with you,
So I can give you 5 minutes. I cannot give you 10 minutes. 8-5. Okay.
okay,
5
sir.
minutes. Okay. And the most important thing that you guys have to be very honest. If you are honest, then I think things will be fine. If you are not honest, things are not going to be fine. Okay. Because the most important that you learn something in this course. I hope you are learning, because these things are new to chemistry student. I'm sure most of you are coming from chemistry. I'm sure it is quite new. And I don't know how many are taking CH408. Anyone is taking CH408 in this semester who is also taking this course? Anyone is there?
Yes, sir.
Who is this?
Neerja.
Okay. So do you think there is an overlap between these two courses?
Yes, sir.
Okay. So it is helping you, no? The other course.
Yeah,
This course should help you to do well in the other course. Yeah, but I think in this course is taught more rigorously, I'm
yeah.
sure. Yeah. Okay.
Sir,
Yes.
sir, can you just reduce some like 11 to 12 lecture in the mid-sem exam?
No, we cannot do anything. Whatever is taught till today, it will be in the exam. So no more request. No more request.
Sir, it is very rigorous for us.
So I don't
Okay,
care.
sir.
I don't care. Who is this? I don't care. Who is this?
Sir Ravi.
Yeah, I don't care.
Okay,
Then
sir.
you should have not taken this course. The courses are like this. If you are spoiled, I don't know why. Courses are like this. You go to any international school, a chemistry department, you take a stat math course, it is taught in this way. Okay, it is this. The subject is like this. Even the quantum mechanics is also taught with a lot of rigor and mathematics. There is no escape. You cannot study physical chemistry without mathematics. I think it is getting recorded. I know, but that's why I'm telling. Physical chemistry cannot be taught without mathematics. If somebody tells you that physical chemistry can be taught with mathematics, I do not agree with that. I don't know about what you think, but this is how it is. Okay. So whatever is taught till today, it will be part of this course exam, which is day after tomorrow.
Okay, sir.
Okay.
Sir.
Yeah.
Okay, sir.
So I'll just now stop recording and